Hello everyone, my hair has been causing problems with the microphone, so hopefully this all works fine. Access Control on Sesame Street, yeah, so Matt Daley, Principal Research Consultant at Or Information Security and General Weirdo. Without further ado, let's begin. Now, two things. We're doing this live. I've only seen this talk once, and so I've seen it one more time than everyone else in this room. You'll see why soon, but I lost access to my slides rather late in the process and had to redo them all last night. So if I seem a bit out of it and I have no idea how much my time limit is going, it's 44 minutes still, great, then that's on me. And this is also a information dump on a bunch of research that I've done over the last few months on Gallagher card systems. So a talk is not the best format for, here's a list of opcodes and here's a list of data types and stuff like that. So after this talk, I'll be releasing information in a more usable format, bunch of documentation and source files. But for now, you get this melange of bad art and information. So let's start with what the average access control system looks like. So you start with a controller. And you usually have on each door, you'll have a reader, an RFID reader, a lock, so like one of those magnet ones, and an input, which will tell whether the door is actually open or not. So it can beep annoyingly when you leave it open. And these are all connected to the controller, usually in, they can be connected directly to the controller, or they can be connected to an I/O breakout. But either way, you'll have lots of those sort of three items connected to the controller or a breakout, and they will connect to the controller. And you might have more I/O breakouts as well. And then you need some kind of administration tool here. So Officer PC is a terrible name. It wasn't the Officer PC. But this is meant to represent the PC that the security guard would use to see who's on site, who's trying to break in, what needs to be attended to, that kind of thing. And then you'll also have a administrative console. So this is where the site installer can install, add new hardware, set up new cards, fix faults, that kind of thing. So it's pretty obvious, really. The idea is that a user will scan their card, hold it up to a reader. Reader will send that information to the I/O breakout board, sends it to them to the controller. The controller has a think to see whether that person is A-OK or not. It says yes. And then usually it's the I/O breakout board. It's the board's job to unlock the door and make the reader say a happy noise. So how does this badly drawn diagram fit within the Gallagher brand access control system? Their marketing material is a lot better than this, for starters. So let's look at the controller first. So the Gallagher state-of-art controller, wow. I just gave you your brand name. Controller 6000 is the current state-of-art Gallagher controller. This chunky brick-sized thing, about this big, and it's scalable, intelligent control, blah, blah, blah. All you need to know is that those green blocks on the side are where you can connect in other devices using protocols that I'll talk about shortly, and the Ethernet cable on the right-hand side there for talking to the administrative consoles. Yeah, okay. And then you also plug in you can also plug in additional plug-in boards from the bottom to, additional, have more doors, for example, it's configurable. The idea is that this is just the top part, then you'll have slide this big chunky thing in the bottom, and then you can have, it's customizable basically. Before this controller 6000, there was the Cardax FT controller 3000. Which comes in green and also fetching red. Now, Cardax was the previous name of this technology, and I will admit I don't know the business background, but I believe they were brought out by Gallagher at some point. So you'll see references to Cardax and Gallagher kind of interchangeably, especially from me, because I don't know which one is considered which. But the idea is that they're interchangeable. It's just brand name changes, basically. And yes, on this board here, that is an Intel i386. So that's the era that we're talking about for these Cardax technologies. I think I'm the only owner, and I don't know, but it took me so long to get this book. This book is helped me reverse engineer some of the firmware on these things, which uses an embedded DOS-based, well, it's an embedded kernel that pretends to be Windows, and it runs on 386 CPUs. And the book is from the era where ARM is an up-and-coming technology, and soon we'll have 32-bit and 64-bit, so that's very cool. Okay, so now that we've seen, you've got your controller, let's have a look at the reader. So this is the current state of art in reader technology with T20. It's like the Terminator or something, right? It does all the things. And then you've got all the other crew. So we've got, long boy, bigger boy, square boy, and but there's reasons to use different ones. T15, for example, is very weatherproof. Yeah. So these are what Gallagher wants you to be using, and for good reason. Unfortunately, what you'll see out there still is from the Cardax era. So this teardrop reader, it's called. And by the way, all the readers have this trademark green squiggle, which is not an S, it's the opposite of an S, as I figured out alarmingly late during all this. But yeah, Cardax reader. Then you've got this bad boy. It's got keypad, does the same thing, but it also has keypad input and nice LCD display. And then you've got the formidable, chunky, good old-fashioned, I don't even know what that's called, Prox Plus, I believe, Prox Plus 125. Now, just as an aside, I got all of these pictures from FCC, FCCID.io. Basically, they take the FCC, the Federal Communications Commission, or whatever it is in the US, takes their god-awful website and turns it into a usable format. So you can, look up companies' registrations. So, for example, here's all of the things that Gallagher's had to register for FCC. And for each of these things, you'll see a bunch of useful information, including user manuals input, user manuals, photos. Most importantly, you get internal photos, which can be really helpful. Yes, I couldn't be bothered rotating it. And I'm very thankful to Dave for doing these things. I don't know why I bothered blanking out the email there. Okay, and then the officer PC, for lack of a better name, monitoring PC, that takes the form of Command Center of Gallagher. I do have an installation at home. As you can see, the only events I ever get is that I've pulled out the controller and plugged it back in again because I'm trying to break something. So there's not much interesting to look at there, and Gallagher will probably be annoyed that I don't show a nice, much more meaningful, interesting display. But this thing can do some pretty amazing things. It can turn on and off your AC, so when someone walks in a room, it does turns everything off and on. You can have it so that people's lockers are controlled by these T20 devices. You can even have a breathalyzer, so people aren't allowed into a room, or they are allowed into a room if they're drunk. So there's lots of amazing things that this thing can do. But 95% of the installs you'll see, it's just annoying people with cards to get into the office. And then the administration PC looks like this. Administration console looks like this. It's that. And you can configure everything here. There's a giant menu called configure, and it has literally everything. So yeah, the Gallagher system, same thing. Controller, then you have breakout modules, and then you have all your readers. There's actually a lot more, as you can see in this diagram, that we could go over, considering it started off from very basic things like this. Now, yes, so why Sesame Street? Might as well get straight to that point. And I only know the top 8 of this grid of people. I don't know the last 4. Orange dude, red dude, freaky brown thing, and blue one. The reason is because those are the code names that they used, as I discovered. Gallagher uses these code names, or Cardax did, and Gallagher still does, for their products. So, for example, the Controller 6000 that I talked about, well, meet Grover. The Cardax FT3000 meet Bert. And the Command Center control platform meet Elmo. And for the I didn't go over these, but the F-series fence controllers, these are used for electrifying fences and telling you when someone's touching them and when you're giving them a nice free bit of electricity. That is code name, this guy. That one. It's Frazzle. I thought Frazzle was a very good name for that, but I'd never heard of him before. So there's a lot of technologies in use. This is just a bunch of information, like I said, that I've scraped so far. You can see there's a range of technologies and uses. I now know more about ARM Thumb than I did before, and I know now more about Intel 8051 and FileApp embedded kernel than I ever wanted to know before. But there's a whole range of technologies there. It's pretty cool. Even the T20s that you see, those are actually running Qt web browser, and they're using WebSockets. So when you press, there's a little JavaScript interface on the front screen. So you press something, WebSocket goes to a native WebSocket client, and then that does more stuff. So real range of technologies all the way back to DOS era stuff. Okay, so as you saw, there was a lot of technologies there, and in the interest of time and me only having a certain amount of it, I've restricted myself to basically things that are accessible by an unauthenticated idiot out on the street. So unprotected stuff. So this is stuff like readers, cards, and the connections coming out of the readers. So intercepting cards, that's cool. Playing with the readers, you'll see that's okay. And pulling the readers out and playing with the connections directly, that's probably a more intense job, but it can be done. So yeah, you could go through the cloud or whatever you want and try and attack those administrative console PCs through the corporate network, good old-fashioned network level hacking. But that's a whole nother talk. I didn't really look at the consoles that much, but to be honest, a lot of sites out there just have them, domain joined PCs with some crap password, and that's the administrative console. So lots of jobs I've gone on, done a network pen test, and there's a PC called Cardax. I wonder what that does. So yeah. Okay, so now let's look at these outlying technologies, the stuff that we can actually play with as a person trying to potentially get our way in. So let's start with a reader. It hungers for a card, but which card does it want? So there's two main kinds of RFID technology, low frequency, which runs at 125 kilohertz, and high frequency, which runs at 13.56 megahertz. Let's start with low frequency. So the implementation of low frequency cards in the Cardax/Gallagher system, I guess it's only Cardax these days, is they're called Cardax procs. I mean, it's hard to tell what they're actually called because it's not really a brand name or anything, but I've called them Cardax procs, and they look like this. So there's no point in me showing the cards because you can't reliably determine the type of card from how it looks. Just to show you, here's my collection of test cards, and see, they all look the same, right? Totally different cards, apart from the writing. Now, if you excuse me for a second, I'm going to steal some slides from a previous talk. So if you see the art style change from one style of bad hand drawing to another, that's because this is the talk I gave at OzSecCon last year on RFID. Just some generic slides that I can use. So there's 4 ways that we can look at RFID technology, physical, data, protocol, and system. So physical, all you really need to know is these cards use the Wiegand effect, which is a cool thing. The reader can provide energy and through a oscillating magnetic field, and basically it's just like an induction. So one side is a magnetic loop with current going through it, moving current in a wire makes a magnetic field, and then moving magnetic field in the coil in the cards does the opposite thing, turns it back to energy, rectifies it, turns it to DC, and then uses power the card. And then the card can also load modulate that RFID field to send data back to it. How heavy is it drawing power? It can be like a 0 or a 1. It's quite cool. And there's different ways of modulating information. So you can take a bit stream, you can then modulate it different ways at a digital level, so Manchester, for example, and then you can modulate it at a different level, at an analog level. So the Cardax proc system uses Manchester encoding, so that's the bottom one there. Basically, all zeros turn into 0, 1, and all ones turn into 1, 0. And it runs at clock speed RF32, which means blah, blah, blah. So it looks like this. When you plot it using the Proxmark software, if I hold up an LF RFID card to my reader, and I can plot the waveform it outputs this. And so yeah, let's talk about the data layer now. So from looking at the administrative console, if I wanted to encode a new card, I can see that there's 4 elements that a Cardax card has, right? So I know from open source research, so by that I mean looking at manuals and figuring out that if it says, like there's 65536, or if it says there's 65,000 of these things, that probably means it's a 16-bit value, for example. So it has a 24-bit card number, a 16-bit facility code, so that's the idea is that card numbers might not be unique, but the combination of facility code and card number should be. Actually, I lied, because it should be the combination of region code, facility code, and card number. And then you have an issue level, which is basically how many times has this idiot lost their card, and how many times have I had to reissue it. You start with 0 and you move upwards from there. So I know that somewhere in this stream of zeros and ones is this data. So here is that streams of zeros and ones. There's clearly a repeating pattern here. I wrote this out for some reason. So when we look at the best way to do protocol analysis is it's like a scientist, right? You think of an experiment. So you take a sample and then you change one thing and redo it. So that was a terrible explanation. Basically, you take a card, encode a card with some known parameters, get the bit stream, and then you'll change just one of the fields, for example, and then look at that bit stream. The idea is you want to see what difference, in what field makes to the bit stream. So what we end up seeing is that this is a common prefix, so this is like a training sequence, just to help the reader realize that there's a card, here, and you should pay attention to the following data. So that's always 7FEA, I think it is in hex. And then we have the last eight bits, which turn out to be, well, I haven't said yet. They turn out to be something. Okay, so what happens is, sorry, slides, remember. So if we change one of the fields, for example, this is what happens if I change the card number up by 1. Okay, we see 8 bits change. That's actually incorrect. It should be 9. But the idea is that we see quite a bit of difference. So what's going on there? So after a bit of head banging, not the metal kind, more like head desk banging, you see that every 9th-ish bit is the opposite of its previous bit. So here you can see, if the previous bit was 0, then the next is 1 and 1, 0. So there's some kind of like parity padding bit. It's not really parity because it's only parity over the last bit, but it's definitely doing a good job of padding it out. And then we can actually eventually see that this last 8 the last 8 bits is actually a CRC of all the data excluding that prefix. So it's got a slightly unusual initialization value and a slightly unusual polynomial value, at least to me. So we now know that the yellow part is some data, the unhighlighted part is the prefix, and the brown pink part is the CRC. So let's remove all these things that we know what they are, and we're left with this still. And now let's convert this to hex. Now we start to see some kind of stuff happening here, right? There's A3s all over the places and A2s. So we do the same thing. We take a bunch of cards, we change some things, and notice the difference. Okay, so even longer later, and I'm not going to explain how, but basically we can figure out what this actual data is. So again, there's 8 bytes. It turns out that the card number is splayed across all of these. So for example, bits 0, 1, and 2 are in the 3rd byte, 3 to 10 are in the 2nd, and so forth, and hopefully 0, 2, 3, 10, 11, 15, 16, 23, yes, okay. So all the card number bits are spread across those 8 bytes. Facility code is here, region code is here, issue level here, and stuff I don't know or care about, but usually way 0 is here. But there's a twist. So what they've done is they've done a simple, I'm not a cryptographer, not the old style, but a substitution cipher, basically, an S-box. So basically, for example, you can see here just that the byte 00 gets mapped to A3. So A3, all those A3s we were seeing in that input data, that data are actually zeros, and that's kind of a good sign. 0 is like probably the most common thing that we're going to see in the underlying data. So we can now decode this from that bunch of data into its underlying fields. So we have the card number. This is the actual data, and I'm very sorry, facility 456 region code 0, but user 123 now has their card data there. So card number 123, facility code 456, region code 0, which is usually written as A, and issue level 1. So this is card number 123 for site A456. That's how you might see it in the consoles. So what do you do when you have the ability to take an existing card, decode it, modify fields, and then re-encode it? Well, you take your work card and try and get onto the roof of your office building. So I miss you, laptop. So we have this thing called a Proxmark, and this is the POC version, right? But eventually it does work. So what we can do is we can take my work card. Our office uses a more secure system than the rest of the outside of the building, landlord versus our tenancy. But sure enough, this works. Eventually, if I increment the card number up enough from mine, that works, cool. Yeah. Cool. So basically, low-frequency cards are busted. They've always been busted in that we can always clone them. Okay, there's always ways to easily just clone them, but now we can go a little bit above and beyond and actually, modify the data that's on them. So you might have a boring, plebeian employee card. Now you can turn that to an administrative card, something like that. So for high frequency, high frequency, there's different kinds of technology, but they're all MyFair brand cards that the Gallagher system uses. So MyFair Classic, MyFair Plus, and MyFair DesFire. So let's start with MyFair Classic. Looks like this, which is an ISO 14443 card, Type A, because there's also Type B, because they couldn't decide which standard they wanted, so they just called two standards, one standard, and called them Type A and Type B, which is ridiculous. Physical, yeah, it does some things. But so it's still weigand. The card gets presented to the reader gives data, power, and the card gives data, but there's a twist. The reader can also give data now as well as the card. So this allows for basically a more interesting form of communication. So MyFair cards don't just spit out, some sequence of bytes over and over. They actually have blocks and sectors, just like a little tiny memory, flash memory card. So MyFair 1K, for example, holds 1 kilobyte of information. So you've got your blocks over here, blocks and sectors. Block 0 always has manufacturing data, and in each of the blocks, for example, this is block 1, sector 1, sorry, the last block in the sector contains 2 keys. Which keys are allowed to actually read that sector? And the access bit, which is kind of like the read-write executable of the Unix world for this. So basically, what key can do what? Can it read this block? Can it write this block? So, for example, you might have your access control data in block 0 of sector 2, and in the key sector of that block, which should actually be 3, not 2, you'll have the keys set so that you can, only read with key A, and you might need an administrative key to read with key B. So this is the first taste of real crypto for some reason, for some definition of real. Both the card and reader must prove knowledge of the shared secret, namely that key. And this cipher is called Crypto 1. Basically, the way it works is the reader says, I would like to read block B. The card gives a nonce back, a number used once, NT, and the reader, in turn, decrypts that nonce, which has been encrypted by one of those keys, to prove that it has it, and then it does a little modification and then re-encrypts it. So basically, it can prove that it could decrypt that nonce, fiddle with it, and re-encrypt it, which proves that it knows the key. And then, in turn, the reader also sends a nonce NR, and the card does the same thing. So it decrypts that nonce, fiddles with it, just rotates it one bit to the left or something, and then re-encrypts it. So these two nonces get modified and sent, and the idea is that this prevents replay attacks. You need the card to actually be there. Is that correct? Moving on. So MyFair Classic, so Sector 0, so let's look at a Gallagher card now, a Gallagher Cardax MyFair card. So MyFair is like a generic technology, and let's see how Gallagher is using it. So Sector 0 has manufacturing info, which is you have to have that there, and then a MyFair access directory, which is just some MyFair stuff which is there. Sector 14 is a thing, but it's not of importance to us. Sector 15 is the one that you can't read with publicly known key, you can't read with no keys. It's locked, so this is the interesting one. Now, this is nothing new. It's been known for a while that MyFair Classic cards are busted. People did some maths and figured out that if you know one of the keys, you can then, using magic maths, brute force all the other keys out. And luckily for us, usually at least one of the keys is a well-known one. So, for example, the read key for the MyFair access directory is, which is highlighted in blue there. It's actually A1, A2, A3. Something like that, but basically we know that, and so we can easily get the key for 6 to 15 using this technique. Those are the keys there. Now, before everyone gets all blah, 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 like I say, it's already in the public, so people already know this, and like I say, the technique, if you have a MyFair Classic card, anyone can do this. So, for example, this person here we recognize that squiggle. He's also noticed those keys before. This is the only other place that I've seen them printed in like a research sort of document. But you'll notice here that he's got that Cardax key thing, and he said, like, these keys by Unix to each individual are generally incomprehensible and a series of various ASCII characters. Without access to the system backend, it can only be assumed how these keys work and what meaning the characters have. Okay, so let's look at sector 15 ourselves, right? This is what sector 15 looks like, that locked sector, now that we have the keys. So you can see there what the keys that are in that sector to tell which ones are allowed to use. We've cracked them, so we can read the sector now. There's the access control bits. I'm not claiming a prize for figuring out that that's ASCII, and that's www.cardax.com // and that just redirects to Gallagher these days. But what's this? Sector very start is, well, we recognize this, right? This is the same kind of 8-byte encoding that we saw for the LF cards. And the last 8 bytes are just the bitwise inverse of those previous 8 bytes. So you've got the 8 bytes, and then you've just got the inverse as well. So basically, we can do the exact same thing. We can take the top of that sector, decode it into the card number, facility number, blah, 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 blah. Same thing. Now, NXP, the creator of MyFair, tried to resolve the situation by removing the Classic from production and introducing the Classic EV1. That got broken, so they introduced the Plus, and then they introduced the Plus EV1. This is a giant mess, so I'm just going to skip all over MyFair Plus, mainly because not many people that I've seen actually use them, and it's very similar to the next. In Gallagher, in the way that it works in the Gallagher system, it's very similar to the way of the card technology, which I'm just about to talk about. So this is the MyFair DesFire. So this is the best current state of art of MyFair cards, for some degree of best. So DesFire. So this isn't a block-based card system, this is file-based. So you can have multiple applications, and each of those applications can have multiple keys, and then each of those applications can also have multiple files. So you can use, the idea is that you can use one card for vending machine, payment, door. I mean, of course, it never ends up like that. It just ends up being a single-use card, but good intentions, right? So this is what a Gallagher MyFair DesFire card looks like. So there's card application, which is always there and it's boring. Card application directory, which is the one on the right, that's boring. Cardax card data application, which you might have multiple of. This is interesting. There's 3 keys there that can be used to access this application, and there's 2 data files there. These are all readable by default. They're not interesting, and you'll find out what they're about if you read my stuff later on. But these we can't read without using one of the keys. So what's in here? So when we look at the configuration settings of the the Gallagher controller setup system, we notice a thing that it's doing a thing called key diversification. So you can input a MyFair site key, and what it will do, I'll just explain key diversification real quickly. It takes an existing key, some other data represented by this database icon, and it merges them together to create a new key indicated by the different lines. So key diversification lets us take a key, some other data, I'm just repeating myself, and turn it into another key. The reason you might, the protocols that they're using for this, the Gallagher's using, it's well known, public AN10922, which is recommended by NXP, MyFair themselves. I did notice, Mr. Gallagher, Mr. or Mrs. Gallagher developer, that I think you broke one of the steps, so you got a bonus step instead of using the standard, but that might just be me. I'll be interested to hear about that. But basically, the Gallagher system lets you enter a MyFair site key. It will then diversify that site key with each card's UID, and those diversified keys are then the ones that are used to lock the application. So to lock the master application, to lock the CAD application, one that's not important, the UID discovery key and the Cardax read key. So the idea is that these keys are needed to read blocks or files on the application. These ones are used to write. So in theory, the reader should only need this single key, okay? Now, but hold on, let's go back and look at that diagram one more time, because you probably already saw it. There's a big giant checkbox that says use default MyFair site key. Now, I know that MyFair default site key, basically, through reverse engineering. So given that we know the MyFair site key, and given that we know any given card's card UID, a card UID is just like a number that it will spit out without questions asked, just a serial number. We can then diversify those and grab all of the other keys. So if a DesFire card is using the default key, it's possible to, you have read-write full access again. So you might ask, what is the key? I'm not going to tell you or show you it. You'll see why that would be a bad idea later. If you're going to ask me how to find the key, the answer is still no, because I don't want Gallagher to throw me into a room of Frazzle units as a product tester, basically. But we can now read what's on those files. So assuming that a default MyFair site key isn't used, we can then diversify that key and read those files. Turns out that the Cardax standard thing just has the usual 8-byte thing and the inverse again. So you can see that this 8-byte thing is used is like a very sort of weak protection on the underlying data, and then it's put in a different container depending on what type of card. But once you know how to decode these, and once you know how to get the keys you need for the card that's holding it, it's game over. Am I going to have enough time for this? No, I'm not. So I'm going to skip right over this. Okay. Now, what are we talking about? Oh yeah, so now let's look at the protocol between a reader and the controller. There's 3 in use: Cardax IV, which is the Yodi one, G-Bus, and H-Bus. G-Bus is medium moldy, and H-Bus is best current practice. There's apparently one called Local Bus, but I have no idea what it is. So H-Bus is the current one, and these ones are the backwards compatibility ones. Start with the Cardax IV protocol. So this is used for these bad buggers, these old ones. It's serial pulse wave modulation, sort of. Very simple. There's 2 wires, one from the reader, one to the reader, and depending on the length of the pulse, it's either a 0 or 1, and it's 5 volts. It's very simple. Looks like that, except that that's got inverted polarity because reasons. So the Cardax IV protocol is pretty simple once you decode it. There's 1-byte opcode and then a bunch of data. So from the reader can send a bunch of opcodes indicating that it's got a card, it's had a keypad press, or it's still there. From the controller, there is a lot more opcodes that the controller can send, to do all the fun things that we love that these readers do, like play the unhappy sound, or play the you're allowed sound, or flash the light, or do whatever. So there's a lot more as well. So what we can do is we can build a tool to man in the middle the protocol between a reader and a controller, just to verify, and this is how you find this out anyway. So we've got from left to right, we've got a power supply thingamajiggy, a Raspberry Pi, a G-Bus I/O unit, which is basically just there because reasons, and then a reader. So basically all you need to know is that the Raspberry Pi is intercepting the comms between the reader and the controller, which is one of the cables going up. Can't see the controller. So it's just good old-fashioned Python on there using PyGPIO, and that's pretty simple. Is this video going to autoplay? Please. Oh, okay, yeah, so you can see there, press button, get that thing, get the card data through that, right? It's simple protocol, nothing there. So what would happen if we were to replace, for example, the reader? So let's try sending our own Cardax IV data instead of letting the reader do it for us. So after all, it's the controller that makes the access decision, the yes/no, not the reader. The reader is just there to gather the data and to annoy you with sounds. It doesn't actually make the decision itself. So I moved from Raspberry Pi to Arduino. That is the only picture I can find. That is my carpet. That is an Arduino. But basically, this is designed for a specific kind of interesting attack, a timing attack. A timing attack is basically where you take advantage of differences in the time it takes for a device to respond to a certain request. It's just a generic technique. So what the Arduino does is it uses interrupts and ring buffers to make message receiving and sending efficient and accurately time-stamped. So what it does is basically it outputs a bunch of JSON, and what it does is it sends a bunch of messages saying, pretending to be a reader, saying card number 1, facility code 1, and then it checks to see when it gets the response saying yes or no, or it logs all of the responses it gets from the controller, and it accurately timestamps them to the nanosecond or something like that. So a bunch of messages being spammed out of different card numbers and facility codes, and different messages coming in. We can then take some more wonderful Python, and we can create a giant mess. And what this giant mess is actually showing you is, for example, how do I explain this? So at every gray line, we were sending, do I have this thing? No. At every gray vertical line, we were sending a new card information message. Only, and I know from the way that I've set up the controller, only one of the facility codes is valid. And we send that valid facility code when it's the green shaded box. So looking left to right at the top, you've got 1, 2, 3, 4, 5, 6, 7, 8 invalid cards, then you've got a valid card, and then 8 more invalid cards. And what the colored dots are the response messages color-coded by type of response message from the controller. So you can see that when we are spamming out invalid cards, you can clearly see that there's a pattern. And then when we're outputting a valid card, you can clearly see that there's a big gap, right, while it's busy thinking. That's because the controller is doing a sort of two-pass thing. It's checking, is the facility code even valid? If it is, then there's more to do. But if there isn't, I can just instantly say, no, go away. So this is basically a generic timing attack. We can send out card data, measure how long it takes for the controller to say yes or no, and then from that, make a judgment call as to whether that was a valid facility code or card number. And then once we have a valid facility code, we can then start brute forcing the card numbers. In theory, this would work, well, it does. It enumerates the entire facility code card number space, so that's 24 plus 16 bits. It does that in 4 hours, which sounds like a while. I won't disagree. Just there's the list of messages, the color codes, and different classifiers. It's hard to, basically there's different, I didn't go full machine learning, but I tried different ways of detecting, given this bunch of messages, was this a valid message or not? And it turns out that the red, there's a very simple predictor of whether it was or not. See if it sends back a message saying turn on your red LED, so that's the orange one. That works in 100% true positive rate, 97% true negative rate, and a 3% false positive rate. So that is, and 0% false negative. So basically, you can see, hopefully, yeah, basically, in every time that we send a bad card, we always get a message saying back, turn on your red LED within a certain amount of time. But when we send a good card that we don't, we have the facility code for, but not the card number, it will not send that so quickly. So we can use that as like a predictor of whether that card was a valid facility code or not, and then start brute forcing card numbers. So the intent, well, it is how it works. This is a Blueno Beetle, which is a very tiny Bluetooth Arduino thing. The idea is that you connect this, pull out your reader, connect the 2 wires you need, 3 wires you need to the pins, and then you can just put the reader back. And this then reports back through your phone, an Android phone, as it reports back progress, how's it doing, has it found the facility code yet? If it has it found a valid card number? And if it has, cool. And then you can just press a button for it to replay it and open the door. Unfortunately, this does work, but I don't have the video for it because of that aforementioned slides issue. But it works, trust me. Yeah, wait, clap, okay. Okay, moving right along, GBus is another protocol. It's a protocol, I wrote a decoder for it. Come on. Moving right along. GBus is another protocol which is in use. You can use this to control the, oh, it is playing, okay, right. You can use this to control the I/O devices. So for example, you can read and write messages to the devices that handle the door, the actual locking and the censoring off, window open or, door held open too long. Was this going to play? Yeah, okay, so Python script is a bit less janky than the other one, but you can see here that it's detected a bunch of devices. It's given me the input of all of the status of all the inputs. I pressed a key, I swiped a card, that sort of thing. So we have that too. Now let's very quickly look at HBus. HBus uses RS485, which is a differential serial thing. It's a protocol, runs at 1 megabit per second. It's pretty fast for serial. It's very simple. There's just 2 voltages. If one's higher than the other, it's 0. If it's the other way around, it's 1. So it's very noise tolerant. The other nice thing about HBus, like GBus, is that you can have star configurations. So instead of having to have each single reader connect, not star configurations, but you can have bus configurations. So instead of having every single reader having to connect to the controller indirectly, you can have them all in a daisy chain, basically. And this is also good because it prevents, if I was to go and try and introduce my own reader, it gets no attention from the controller because it has a special protocol for assigning new devices. So basically, any new device that's connected will say, please give me an address. And that's where it stops until a manual event occurs where an administrator on one of the admin consoles manually says, yes, this is a device I trust and I want you to start using it. So you can't just go in, jack in a reader, jack in a dodgy looking box thing and expect that you'd be able to talk to the controller. There's a bit more to it. It first needs to be approved by an administrator, and then there's also more. So let's say it did get approved by an administrator, it gives an address, that's cool. Next thing is the new device says what protocols it supports. In this case, if it's new, the controller needs some new pre-shared keys, so it asks for that protocol. They exchange public key certs, so yes, each device basically has a public key certificate. Nothing sensitive here, it's just public keys. These are all signed by Gallagher, so basically each device, you can see there the serial number is actually the ASCII version of the serial number actually of this reader. This is a reader's device certificate, I believe. So basically, there is an authoritative chain of trust basically between Gallagher and its devices. More things happen, and we end up with a set of keys. And then those keys, now this device is registered, we can now say that we want to start an actual data transmission protocol. We can then use these keys to prove that we can respond to a challenge, and then we can then use all of these keys to then exchange data. So that was out of order. Anyway, so you're asking where's the fun vulnerability in HBus? Well, there isn't one for now. Why did I tell you about it then? I want to prove the difference, but show the difference between the current tech offered by Gallagher versus the ancient Cardax IV and GBus, which are very broken, basically. Of course, I would like to look at HBus more, and I will be. That's all I got up to in this current time. So we've looked at the cards, the readers, and I didn't find anything in the readers, nothing that I can tell you about yet. So I did look at the readers. So I've talked here about the cards and the connections past the readers, and I looked at the readers myself. There's one missing element here. That's the actual RFID data transmission. So there's two forms of RF-based attack. There's skimming. So skimming, and that is not a balloon, that is a magnetic loop antenna. So like I said, magnetic loop induction, wonderful. So the loop, if we're doing a skimming attack, that's when we walk past someone, power up their card, and retrieve the data off it. So our antenna powers it, we exchange data, and grab the data off the card. Now this works fine for our low frequency ones, because as soon as they're powered, they will just start screaming out that magic number over and over. There's no access control, there's no protocols, it's just power, and it starts modulating the number. So we can put an antenna into that field, and then spit that out to any old reader, save it or do it on the same spot. That's a replay attack. But this doesn't work for high frequency, 13.56 megahertz, because of a little thing called physics. Basically, the power required to, the magnetic field strength required to power a higher frequency card is a magnitude, well, I'm talking stuff I don't understand, but it's a lot more power required to power one of these cards from a reasonable distance than it is for low frequency. You might have noticed that, like old readers, low frequency ones will accept the card from quite a bit of further distance than the newer high frequency ones do. How it is. So instead of skimming for high frequency cards, let's try intercepting them. So intercepting is similar, but basically we're intercepting a transaction between a real reader and a real card. Kind of like how the agency, has its spy bases, looking at downcoming satellite traffic kind of thing. We're just sitting alongside an existing transaction and taking advantage of the fact that the signal is actually going further than it should be. So this is a terrible picture, but this is what a long-range reader looks like when I'm poking it. These only will read RFID 13.56 cards about 50 centimeters. So they're used for car park kind of situations. Just to show you that these do try to pump out a lot of power. They try to make the distance as long as possible. There is I've just put on my sofa a completely unconnected long-range reader, and there's two other different kinds of long-range reader there on the right. I power the two ones on the right, and that's enough to power the one on the left. So they're trying, right? When you open them inside, it says high voltage, and I trust them, there's capacitors everywhere and stuff I don't understand. So it's not through a lack of power that these things are low, it's just physical limitations. So what can we do? Well, normally readers, what they'll do is they say, please give me block 60, the one with the magic 8 bytes in, and the card will give the block data. The reader has to treat all the blocks the same because the reader doesn't necessarily know what the content of the data is. It just needs to pass it on to the back end. It can't make any assumptions about the data. So for example, if one of the bits in that response gets munged because of RF noise, the reader basically has to throw away the whole message. The parity gets corrupted, checksums gets corrupted, whatever, it just can't figure it out. But we know the format of we know the format of the data, for example, in a MyFair Classic card. So for example, if this byte gets trampled on by my neighbor's fridge or whatever, sending out RFID spam, RF spam, hopefully not RFID spam, we can correct it using the conveniently placed, and this is why it's there, we can correct it using the data on the other side. Just flip that bit and now we know what it was. In addition, we can go above and beyond. We know what the underlying field should be. And we know that, for example, if we've lost the bits that would represent the facility code, the high order bits, we know that those are probably zeros anyway because there's not only so many facility codes. So what we can do is we can just replace that with data that we already know. So using HackRF, that's a software-defined radio, and GNU Radio, which is software-defined radio framework, we can make an unholy mess again. But what this does is basically reads in data from the software-defined radio antenna and does a bunch of pre-processing and then puts it into a custom written block there. What this custom written block does is it can look at only the bare minimum amount of messages that we care about just to get a valid Cardax access credential. The reader normally has to say, I want to authenticate, okay, blah, 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 blah. I want this block, okay, what's your CSN, blah, blah, blah. All these messages, we don't care about that. All we want to see is the magic 8 bytes in a transaction. So we only care about the two nonces that the reader and the card give, and the block request from the reader and a response from the card. And we can also do things like, we can take advantage of an offline attack. So normally readers have to be quick, they have to try and figure out what your card said very fast, because otherwise you're waiting there holding your card. We can do offline attacks, we can sniff traffic and then spend longer time trying to resolve any errors in the RFID signal, trying to flip. So what this does, for example, is it flips all the bits in a bunch of various patterns, trying to fix all the parity, for example. And here is more code. So this is what it looks like. You can see there, that's how strong like a reader signal looks like, and that weak signal on the right there, that's a response from a card. Card responses are they're a lot weaker than the reader signal. As you can see there, the reader said a 6000F57B, which is, I would like to do something. I can't remember what 60 is, but I'm sure it's great. So what we can do is we can take the software-defined radio, put an antenna on it. There's my magnetic loop antenna. Hold it in front of a reader, and basically we can see how far can we see card-reader interactions. This works only about 30 centimeters, so well done, Matt, you did worse. But in this case, physics actually has an answer. Bigger is better for RFID antennas. So with that in mind, introducing RFID, near field RF technologies are usually just brute force. You don't have fancy antenna like configurations and weird patterns and grills. It's just more metal basically and bigger. So in this case, 1 square meter of copper tubing from Bunnings and a lot of burnt fingers later and solder mess. We have this. Oh, okay, you're showing that. Yeah, that's just the cables. This is taken out of the HF antenna cookbook from Texas Instruments. Here's me and Valentinus, a friend who we borrowed his man cave, I guess. Looks like this, multimeter for scale. This gets up to 3 meters. Now, I know what you're thinking, like, you can walk down the street with this and then, there is a happy medium. And the other thing is, like, there is the opportunity to build a slightly more reasonably sized one. And I'm not an RF engineer, so there's a lot of shit that I had to guess here. I think I got it right, but there's a lot more tuning and stuff that could be done. So if you're an old ham or you work in RF fields, give me some help, that'll be awesome. Okay, so we get to the second to last part because it's telling me time is up, so I'm going to go real fast. This is a danger zone, so don't do anything that I did. Don't do any of this. So I wanted to find out what are the number of technologies in use across actual readers, right? Do a field survey. So I wanted to find out how many readers accept 125 cards, how many readers accept Classic, Plus, and DesFire. Now, Plus is, like I say, the bastard child that I don't care about. It's effectively the same as DesFire, so I'm just going to pretend that it doesn't exist. And more importantly, I also want to know, are people using default keys or non-default keys? Because, as you figured, the only secure configuration is not to use low frequency, not to use MyFair Classic, not to use MyFair DesFire for default key, but you have to use MyFair DesFire with a non-default key. That's the only chance that you have of keeping your credentials secure. Or MyFair Plus with a non-default key. But like I said, it doesn't exist. So I wrote I wanted to know this, so here I am debugging some code out in the middle of the street. I wrote a little, you can't see it, unfortunately. It's just a Proxmark that connects to my laptop and tells me, what card technology is in use on a reader, and are they using a non-default key or not. Important. It does not tell me the key if it's non-default. Because of the way the DesFire protocol works, I can tell if it's using the default key, but I can't. If it's using a non-default key, I can't tell what that key is, but I can tell that it's not the default. So, in my opinion, no damage done. I just get to see what I'd be able to do by holding up my cards, seeing if they ding or not. And the results. So I did a sample of 95 readers. 10 of them they were big boys, 11 Prox Plus, 10 teardrops, 528, 920 of the big ones, and then 2 probably where I forgot to record that information. Low frequency is in use on 35 out of 60. I really probably should have put percentages, but whatever. 35 out of, no, not out of 60, 35 out of 95. That's a lot. And high frequency is accepted by 80 of them and not by 15. So one of the things you can tell by just having low frequency enabled is that it accepts 125 kilohertz Cardax procs. That's by design. The reader doesn't emit a low frequency field unless it's willing to accept those cards. So just by the presence of that field, you know that it's accepting those cards. Whereas for the high frequency ones, you have to actually tell what kind of card it accepts, and that's kind of harder to tell. This is the thing that I skipped over, so I'm not even going to show you that. Okay, so now we get to the big thing. How many sites are using a non-default MyFair site key, right? This is the key thing that is required. Gallagher acknowledges it, knows it. This is the thing that is required to have any form of card security. Put your hands up if you think it's above 20. Above 10, above 5, above 1, 0. Yeah, you have a little faith. Okay, there's 1. And this one particular government department does not want me scanning their readers. And I understand. This is the second time I've had a laptop confiscated by the New Zealand government. So, in my not defense, yes, it was late. I'm a night owl, so walking around in near black at midnight scanning readers, not the smartest of ideas. Just one of those, thinking without, actually thinking too far ahead things. But yes, I would like to point out that if you did see me, and that agency that does know who they are, no card data has been taken. There's no way that can be done. And to be honest, congratulations for having the only non-default site key in all of Wellington. And that's what pisses me off. It's only because of the non-default site key that I stayed around. I was like, wait a second, that can't be right. And that's when the security guards show up and the cops. So yeah. Okay, that was all about attack. Now let's talk about defense. So migrate to a secure card technology, right? That currently is only MyFair DesFire. Gallagher does support Bluetooth credentials and PIV for you Yanks and also people who do use those kind of technologies. But for most of us, it's going to be MyFair DesFire. Disable unused card types. You can do this. You can go to the control settings of each reader and say, I only want you to accept DesFire cards. It's very simple. You know how to use checkboxes. Use a non-default MyFair site key. Uncheck that box, press the handy dandy to generate things. Don't just type in zeros. Press the generate the keys. Now, this is where it gets sticky because you do have to reissue your keys, cards. And yes, like I was talking to contact at Gallagher, and he said, yeah, this can be a problem. And I was like, yeah, issuing 100 cards must be quite a bit. And he's like, try 10,000. And I was like, yeah, okay. So, we're pretty small sites here, but some of the bigger sites that Gallagher do, it is actually there's a bit of stuff that needs to be overcome there first. Use HBus, not Cardax IVG bus, and make use of all the functionality in Command Center. Now, you might be asking, how do I actually audit all this? Well, lucky for you, there is the Gallagher Security Health Check. This is a concerned person looking at his Gallagher Security Health Check report. But basically, you run this tool on your machine, one of your admin machines, collects data, you send that to Gallagher, they run the secret source, and they send you back a report that tells you what your setup is. So basically, this puts me out of business, right? Industry first, automated method to check your security system. We all know Nessus, we all know all the other boring, checkbox standard things. This is first one for actual physical security control systems, which is really great to see. This is what one of the reports will look like, and you can see here clearly that it's talking about the things that I've already bugged everyone about. So reader 125K, you have low frequency enabled, disable it. You have MyFair Classic enabled, disable it. I believe there's also ones for you have a non-default key, don't use a default key. There is also the Gallagher Controller 6000 hardening guide and the Command Center hardening guide. You should read these documents, or your installer should have read them for you. Okay, so that's it. I'm well over time. Now, as I said, this is just a short summary of the sort of more interesting parts of the research. There's a lot more out there that I need to gather my notes for, literally. The best form to find this is I'll probably have this on my GitHub at some point. I'll just make a repo and dump a bunch of information there. You just go to my website, and it's plain in I2P there. And yeah, thank you very much to Daniel Underhay, best friend, and he's given me lots of ideas and support through this. Robert Cowsley at Gallagher. I've put Gallagher through a bit, and this is Gallagher. Gallagher really wants to be the anti-HID, okay? Everyone knows Amun-Ra or whatever it is. The guy leaked the HID I-class master key, moved to China, apparently. They don't want to be that. They want to be supportive. They offer licenses, they offer hardware, they offer training, so this is really good. I'll admit that I wasn't able to keep my bug side of the deal quite so much because these slides, this will be the very first time that they've seen them as well. Apologies, guys, but hopefully there's nothing in here that didn't already get mentioned. But yeah, Robert's been great. Whole Gallagher team's been great. Oh, there they are. Tom Moore, or InfoSec. I've been disappearing into a black hole quite a bit over the last few months instead of doing my work, and it's Tom's job to whip me back into shape. So thank you very much, Tom, for keeping me on track and also for reaching out to that agency to see what could be done. and Aura InfoSec, and you. Also, Vales for letting me borrow your logic analyzer for the last 1.5 years. I still need it, though. Thanks.